This talk is about deterministic leader election in anonymous radio networks. I'm Avery Miller, and this is joint work with Andrzej Pelc and Yadav. Here's a quick outline of the talk. I'll start with some definitions of the model and motivate some of the questions we wanted to answer with this research. After stating these problem statements, I'll go over the results that came out of this work. Then I'll give a few of the high-level details and proof sketches, and finally, a summary and some future work. We'll be using a standard abstraction of radio networks often seen in the computer science literature. So a network is represented by an undirected graph. Each vertex in this graph corresponds to a node of the network, and an edge represents the fact that two nodes are within communication range of each other. So there's an example of a graph that could correspond to a radio network. And operation is synchronous, so each node in this network has a clock. These clocks divide time into time slots, and the time slots are aligned across all the different nodes, although there's no assumption about global slot numbers. In each slot, each node has to make a decision whether it's going to be in transmit mode or it's going to be in listen mode. And the outcome of these decisions is based on the following rules. So if a node is in transmit mode, it will receive nothing during the slot in which it's transmitting. And we're going to represent this using kind of this empty set notation inside parentheses. If a node is listening and it has no neighbors in the network that are transmitting, once again, it will receive nothing. So this is again represented by the empty set in parentheses. If a node is listening and it has exactly one transmitting neighbor in the network, then it will receive the message that is being transmitted by that neighbor. And this is represented by an M inside parentheses, where M is the message that is being transmitted. And finally, if a listening node has two or more transmitting neighbors in the network, then it also receives nothing. It doesn't receive any messages, but it will detect that a collision occurred. And this is represented by an asterisk inside the parentheses. So let's just look at a quick example to solidify these concepts. So let's assume that in our network, the three nodes with towers on top of them are transmitting in the current slot. And those are the messages X, Y, and Z that those nodes are transmitting. And according to the first rule, we know that anybody that's transmitting receives nothing. So that's represented by the empty set. This node up here doesn't have any transmitting neighbors, so it also receives nothing. Here we see the neighbors of Y that have no other transmitting neighbors, they receive Y. This node down here with that only has Z as a transmitting neighbor will receive Z. And finally, this node here that has two transmitting neighbors, transmitting X and Y, receives neither of those messages but detects a collision. The task we're interested in solving is leader election. And so to solve this task, what we're going to have is each node running a local algorithm. Eventually, each node is going to terminate its local algorithm, and upon termination, we require that exactly one node has its leader variable set to 1, and then we'll have all the other nodes set their leader variable to 0. And so there's just a valid outcome of a leader election algorithm, and we're going to be considering a particularly restrictive scenario in which the nodes are anonymous, so there's no IDs that the nodes can use in the execution of their algorithm, and they're all running the exact same algorithm. Further, we're assuming that the algorithm is deterministic. So all decisions, all actions are based completely on the history of the execution so far. So there are no random bits that the algorithm can use to sort of break symmetry or anything. You're probably thinking, wait, that sounds impossible. And it is impossible. I mean, consider any network, or in particular this very simple network, consisting of two anonymous nodes connected by an edge. And consider any algorithm you can run on these nodes and assume that the nodes start this algorithm at the same time. There's really only two possibilities in every slot. Either both nodes decide to listen, in which case nobody receives anything, or everyone decides to transmit, and by the definition of the model, nobody receives anything. And so the histories of all nodes are going to be identical, and so there's really only two possible outcomes, neither of which are valid for leader election. Either both nodes decide to be non-leader, or both nodes decide to be a leader. And so what we could conclude is that as long as the nodes start the algorithm at the same time, it's just not possible to solve leader election. And so what we're going to consider is if nodes wake up or start the algorithm at different times. So certainly if we think about practical real-world situations, it's quite unrealistic to assume that all nodes in a radio network are going to be powered up at the exact same time, or that their algorithms are going to start executing at the exact same time. And so we're going to build this into our model and assume that there are wake-ups. And so what happens is that a node wakes up, and what it's going to do upon wake up is initialize its local clock to 0, and then it's going to start running whatever algorithms installed at that node in the next slot, so in time slot 1. And this is why, when I was defining radio networks earlier, there was no assumption that there's a global slot number or global slot number, because we're going to be assuming that nodes can wake up at different times and start running their algorithms at different times. And there's going to be two different notions of wake up in our model, and each node is able to distinguish what kind of wake up occurred. So the first kind of wake up is a forced wake up, and this happens when a node has a neighbor that transmits, and so when a node receives this message from its transmitting neighbor, it's going to wake up and start running its own algorithm. So that's called a forced wake up. And the other kind of wake up is called a spontaneous wake up, and that corresponds to when a node has a pre-scheduled wake up time, and it's not forcefully woken up by a transmitting neighbor. It's going to wake up and start running its algorithm at that pre-scheduled time. And so what this means now is that our networks are going to have a lot less symmetry. So let's go back and consider this two-node network right here. So once again, these are anonymous. They're running the same deterministic algorithm, and they're going to run the following algorithm. So if I'm a node and I woke up via a forced wake up, what I'm going to do is I'm going to set my leader variable to 0, and then I'm going to terminate. And if I wake up spontaneously or at my pre-scheduled time, I'm going to set my leader variable to 1, and I'm going to transmit some message. Doesn't matter what it is, and then I'm going to terminate after that. And so if you think about this, if these two nodes don't wake up at the exact same time, this algorithm will solve leader election. So one of them will output 1 and the other will output 0. Okay, so to generalize this idea, to incorporate it in our models, we consider something called a configuration. And so we're going to consider the same radio network as defined earlier, but now each node has a scheduled wake up time. And how we represent that in our model is that we're going to have tags on the nodes. So whichever node or nodes have the earliest scheduled wake up time, we're going to tag those with the integer 0. And then for all other nodes, we're going to tag them with an offset. So basically a positive integer that represents how many slots later they're scheduled to wake up spontaneously. And just in a new definition, the largest tag that we give in the network, we're going to call that the span, and that's denoted by the Greek letter sigma. And we also have to remember that this is just an abstraction for our own purposes of the model. The nodes themselves in the network and in the execution of the algorithm, they don't know what these tags are. All they know is that they've woken up and that they started their local algorithm. None of this configuration stuff is available to the nodes themselves. And so here's an example of some tags. So in the upper right here, this node is the first node that's scheduled to wake up spontaneously, so we tag that with a 0, and then everyone else is tagged with an offset, so its neighbor here is scheduled to wake up spontaneously 9 slots later. So now let's think about solving leader election in configurations. There are certain configurations where leader election will be impossible to solve. For example, in this simple situation where both nodes have tag equal to 0, this corresponds to the earlier situation we saw where we concluded that no algorithm could elect a leader. And so if we have a configuration where no deterministic distributed algorithm will solve leader election, we're going to call this configuration not feasible. On the other hand, in configurations like this, leader election is solvable. So if we have a configuration in which there does exist a deterministic distributed algorithm for leader election, we're going to call that kind of configuration feasible. And just as a review, how we can solve leader election, this was the algorithm we saw earlier. And the point is that the node with tag 0 is going to spontaneously wake up. And then after it wakes up, it's going to transmit in its first time slot. And that transmission is going to forcefully wake up the other node that has tag 1. And then so the spontaneous wake up node is going to set its leader variable to 1, and the forced wake up node is going to set leader to 0, and leader election will be solved. So now we can go ahead and talk about what kind of questions we want to be able to answer about leader election in configurations. The first type of question involves feasibility. So can we efficiently determine whether or not a given configuration is feasible? Can leader election be solved in the configuration that's given to us? The second type of question is about leader election algorithms. So even if we restrict attention to only the feasible configurations, is it possible to construct a leader election algorithm for those feasible configurations? Let's discuss the answers to these questions. First, let's talk about the bad news. We proved that there is no universal distributed algorithm that elects a leader for all possible configurations, even if we restrict to 4-node networks. So basically what this is saying is that there's no hope of constructing a single algorithm that can solve leader election in all of the feasible configurations. And so we're going to have to think about dedicated algorithms that work for specific configurations or for specific classes of configurations. We also have lower bounds on running times. So we prove that there exists an infinite class of 4 node feasible configurations, such that for each configuration G in this class, every dedicated leader election algorithm specifically for G will take time big omega of sigma. So what this is saying is that even if we consider very small networks, the span of G will have an effect on the running time of an algorithm, even if it's specifically designed to work for that network. Similarly, there's an infinite class of n node feasible configurations with sigma equals 1, such that for each configuration G in this class, every dedicated leader election algorithm for G takes time big omega of n. So this is sort of the other side of the coin. If we take n node configurations, even if the span is really small, so the wake up tags are all very small within sigma equals 1, the running time of the algorithm on the configuration can still be at least n, which is the size of the network. And so that's basically what this is saying. Independently, both the number of nodes and the span of the configuration can be lower bounds on the number of slots needed to solve leader election. With regards to characterizing feasibility, we have a result that says that there is no distributed algorithm that can decide whether or not the configuration is feasible. And this is under the assumption that the nodes have no initial knowledge about the configuration when they start running the algorithm. So to elaborate on what this means, what a correct distributed algorithm would have to do is that all of the nodes would have to output yes if the configuration they're in is feasible, and at least one of the nodes would have to output no if the configuration they're in is not feasible. So that was a lot of bad news. Let's go over what we can actually accomplish. So we proved that there is a polynomial time centralized algorithm, and we'll call this algorithm classifier, that decides if a given input configuration G with maximum degree delta is feasible. So in particular, if leader election cannot be solved on the configuration G, then classifier will output no, and it will do it within big O of n cubed delta time. If leader election can be solved in configuration G, classifier will output yes within big O of n cubed delta time, but we're also guaranteed the existence of a distributed algorithm that will solve leader election in the given configuration, and the number of time slots used by that distributed algorithm is big O of n squared times sigma. So now I'd like to give you some intuition about why these results are true, and perhaps entice you to go and check out more of the details in the paper. So first, let's consider the impossibility of having a universal algorithm that solves leader election in all feasible configurations. So to prove by contradiction, let's assume there is such a universal algorithm U that's always going to solve leader election in every feasible configuration, and we're going to build some very simple configurations that look like this for every positive integer m. And so these two middle nodes are going to have a wake-up tag of 0. The leftmost node is scheduled to wake up in m slots later, and the rightmost node is scheduled to wake up m plus 1 slots later. Okay, and every configuration that looks like this for every positive integer m is feasible. And so you can pause and think about why that is and try to come up with a dedicated algorithm that will elect a leader, or you can simply read and test out the following algorithm that I've written there. Okay, but more importantly, let's think about what happens when you execute this algorithm U on any such configuration. What we know is that there has to be a time when the middle nodes, these nodes tag 0, there has to be a time where they eventually transmit. And if that's not the case, then it's easy to see that no node will ever transmit. And if no node ever transmits, then everyone's history will be identical and no leader will ever be elected. And so then once you have this time t, you could think about this configuration here where the two middle nodes are tag 0 and the leftmost node has tag t, rightmost node has tag t plus 1, and you can run the algorithm U on this particular configuration. And what's going to happen is that when these two middle nodes transmit in time slot t, that transmission is going to forcibly wake up the two outer nodes, and so they're going to wake up at the same time instead of at different times as they were scheduled. And so from then on, everything's going to be symmetric. The two middle nodes are going to have the same history. The two outer nodes are going to have the same history. And so leader election will never be solved because no node will ever have a unique history. Next, I want to quickly sketch the impossibility result that proves that there's no distributed algorithm that can classify whether a configuration is feasible or not. So it's going to be very similar to what we've seen on the previous slides with these configurations, where the two middle nodes have tag 0, leftmost node has tag m, rightmost node has tag m plus 1. And we're going to consider all these configurations for m greater than or equal to 1. And then we're going to assume there's some distributed algorithm D running in these networks. And similarly, we know there must be a time t when the nodes tag 0 eventually transmit. We're going to consider the first such time t. Okay, But then we can set up the following two configurations, which will be indistinguishable to all nodes running algorithm D. And the reason why these two configurations are indistinguishable is that in time slot T, in both cases, the two middle nodes are going to transmit. And that transmission is going to result in a forced wake up at the two outside nodes. And that's true for the top network, that's true for the bottom network. And so really the executions in both of these networks are going to be identical from the point of view of all nodes. Except the first network at the top here is feasible, and the second network here at the bottom is not feasible. And there are easy proofs to show both of those things, and that proves that D will make a classification error on at least one of these two configurations. Next up, I'll talk about the big omega of sigma lower bound on leader election. So we're going to consider the same configurations as on the previous slide. So let's think about this path configuration like this for any positive m. And sort of by definition of span, sigma is equal to m plus 1, because m plus 1 is the largest tag. And then once again, as argued on the previous slide, there must be a first time t when these nodes tagged 0 in the middle of the network decide that they're going to transmit something, because otherwise nobody ever transmits and everyone has the same history. And what's the value of t? Well, if t is at most m, then we have a situation like I described on the previous slide, where the two outer nodes get forcibly woken up in the same round, and then there's complete symmetry. The two middle nodes have the same history, the two outer nodes are always going to have the same history, and so there can never be a unique leader in the network. So we can conclude that t has to be strictly greater than m, and that tells us that the running time of the algorithm must be at least m, and m is big omega of sigma, so that's basically the proof right there. Next, we'll consider the big omega of n lower bound. So now the configurations are going to be a bit more complicated, so for every m greater than or equal to 2, we're going to construct a path as follows. We're going to put m nodes on the left end, all with tag 0, m nodes on the right end, all with tag 0, and then this segment in the middle of 2m plus 1 nodes, all of them having tag equal to 1. Okay, so by definition, the span is equal to 1, and the size of the network is 4m plus 1. And perhaps what's more difficult to verify is that every configuration of this form is feasible. So you could pause and try to think of an algorithm that will work. Or we could use the following algorithm. And I'll quickly go over this. What we do is proceed in phases. Every phase has 3 slots. And during the first phase, every node will transmit in the middle slot, so slot 2, and it'll just transmit some hello message. And then in all subsequent phases, a node will transmit the hello message in the middle slot if it received a message during the previous phase. And then after doing this for m phases, a node will set its leader variable to 1 if and only if it never received a hello message. So just intuitively how this is working, there's going to be a hello message in the first phase received by kind of these two nodes at the border of these segments, so this 0 and this 1, and at the border of these two segments, this 0 and this 1. And then in each subsequent phase, the hello message propagates towards the ends of the network, but also towards the middle of the network. Due to collisions, the middle node in this path is never going to receive any message, whereas all other nodes on the path will eventually receive the hello message, and so the middle node on this path will be elected as the leader. To prove the lower bound, there are 2 results you can prove by induction about symmetry in this network. The first is thinking about the ith node starting from the left end and the ith node starting from the right end. Those 2 nodes are always going to have the same history no matter what time slot you think about. So essentially there's an axis of symmetry going down the middle of this network. And also, if your algorithm has been executing for t rounds, you could prove that there's this segment in the middle of the network where all nodes have the same history. And so the number of nodes in the middle here, 2m plus 1 minus 2t, nodes in the middle will all have the same history. And so what we can conclude is that if there's going to be a leader, there has to be a node with a unique history. And so the t has to be large enough for this to happen. And kind of doing the math, you conclude that t has to be at least m. The value of m we know is n minus 1 over 4, just rearranging this equality over here. And that's big omega of n. Finally, I'd like to talk a bit about our positive result, which is about classifying feasible configurations. So just as a reminder, we have a centralized algorithm that we call classifier, and it takes a configuration G as input, and it efficiently determines whether or not G is feasible. So whether or not there exists a distributed leader election algorithm for the given configuration. And the way classifier works is that actually if it's a yes instance, so there is a leader election algorithm, really without any additional work, we can extract or figure out what the distributed algorithm is that will solve leader election for G using the execution of classifier. Okay, so that might make more sense as I talk about it a bit more. So at a very high level, here's how classifier works. So it takes in this configuration G, And then what it does is it designs one specific distributed algorithm for the given configuration that's going to attempt to solve leader election. And this is going to be called the canonical algorithm. So what classifier does is it takes this distributed algorithm and simulates its execution on G. And then while it's simulating the execution, what it's going to do is partition the nodes of G into equivalence classes. And these equivalence classes are defined based on the node histories. So two nodes are put in the same class if their history in the execution so far is identical. And then once the simulation of this canonical algorithm is finished, classifier is going to look to see what the equivalence classes look like. If there is at least one equivalence class that contains a single node on its own, then that node can be elected as the leader. It has a unique history in the network. And so in this situation, classifier will output yes, since the canonical algorithm that it's simulated demonstrates that G is feasible, because a leader can be elected. On the other hand, if classifier looks at all these equivalence classes and sees that all of them contain more than one node, then that means no node can be elected as a leader using the canonical algorithm. Because all nodes in the same class have the same history, so if all the classes have more than one node in them, there can never be a node with a unique history in the network, so no leader can be elected by the canonical algorithm. And in this case, classifier will output no. All right, so that begs the question, is classifier correct? And probably by now there are some alarm bells going off in your head, because classifier is simulating one specific distributed algorithm on G. It sees that this specific algorithm cannot elect a leader, and yet the classifier concludes that no distributed algorithm can solve leader election in G. And so this is really kind of where I think the most interesting part of the paper is, because rather than needing to simulate or figure out whether every distributed algorithm on G could elect a leader or not, the classifier is just trying one particular algorithm and then basing its conclusion on that. And this really depends on a key technical result, which states that the canonical algorithm that classifier is using is designed in such a careful way that no matter which algorithm A you're considering, the canonical algorithm will break symmetry at least as well as A does. Okay, so specifically, and perhaps more precisely, if the nodes of G execute an arbitrary algorithm A, and then when A terminates, if two nodes V and W have a different history in the execution of that algorithm, then these two nodes V and W will also have a different history upon termination of the canonical algorithm. Okay, so that's really the key insight here, is that the canonical algorithm is essentially breaking symmetry at least as well as any other algorithm could. And so what that means is that if your algorithm A could solve leader election, then so could the canonical algorithm. The node that has a unique history after running A will also have a unique history after running the canonical algorithm. The converse of this statement is that if leader election cannot be solved by the canonical algorithm, then that means leader election is not solved by the given algorithm A. Okay. And so that means that if classifier outputs no, then G certainly is not a feasible configuration. Since this statement, the above statement, is true about an arbitrary algorithm A, then this just implies that you have to just check if the canonical algorithm will solve leader election. Okay, so to quickly conclude, we have a bunch of bad news. There's no universal distributed algorithm. There's no single distributed algorithm that is going to be able to solve leader election in all feasible configurations. Also, there's no distributed algorithm that can decide whether or not a configuration is feasible. For good news, we do have a centralized algorithm that, if you provide a configuration G as input, will efficiently determine whether or not that configuration is feasible. Can leader election be solved in that particular configuration? Also, if that classifier algorithm, that centralized algorithm, does output yes to tell us that the configuration is feasible, it also tells us about a dedicated distributed algorithm for that configuration that will solve leader election. With regards to future work, we proved via our lower bounds that even dedicated algorithms for some configurations require big omega of n plus sigma slots, since n and sigma are both independently lower bounds. But our dedicated algorithms, the ones that classifier tells us about, use big O of n squared times sigma slots. So there's quite a gap there that could be closed. And with regards to the centralized algorithm that determines feasibility of a configuration, our algorithm runs in big O of n cubed times delta. And obviously there's the question of, could it be done more efficiently? And thank you. If you have any questions, you can ask us in the Slack channel.